Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at Cadence with Prakash Madhvapathy. We're going to talk today about cache coherency in audio. Prakash, we've been dealing with audio for years. Why do we need cache coherency now, and what's changed?
Great question, Ed. Yes, you're right that audio has been around for a long time, and there are devices out there with DSPs in them. But the performance requirements for all of the DSPs are going up. Why are they going up? Because people want to offer higher performance and higher quality to consumers. And when they do that, they require more performance in terms of cycles and DSP processing. Now, what does it mean to DSP architects? They have to instantiate multiple DSPs in the system, in the SoC. How do you coordinate the software running across all of these when audio has to be split across these DSPs to complete the entire audio chain of processing? That is a difficult part. They try, they do fairly well, but there are problems with scaling that approach and other issues with reliability, etc., that come with it. So that's why cache coherency is required to make life easier for architects and software engineers to enhance the performance of audio in their end devices and also to scale to higher performance for greater functionality and quality to consumers.
Let's take a closer look.
Sure.
Prakash, what's the difference between a coherent system versus a non-coherent system?
So here we're showing a non-coherent system on the left-hand side where there are two cores, which are DSP cores in this case, each having their own tightly coupled memories, and both of them connected to a level 2 memory to be able to share data and control code, etc. We will focus on data, for this aspect of it. So what happens in a non-coherent system is that when you have data that is being shared between two cores, because the algorithm is split across both cores, maybe one acts as a producer, the other acts as a consumer of that data, you have to have a unified view of memory. How do you achieve that when the entire system is non-coherent in terms of hardware? So let's take an example here. Here's a variable, the value 5 in memory. Let's forget about the data type. It's just 5 at the moment. When core 0 reads it, it gets the value 5. When core 1 reads it, it also gets the value 5. Okay. Now, core 0 updates the value in its local TCM from value 5 to value 6. Okay. So now he sees that the variable v is value 6. But the L2 memory has a value 5, and core 1 has a value 5. Already you can see that both cores have become non-coherent with each other. So they don't have the same view of memory or the variable value in memory that they had before any one of them updated the value. So when that happens, all hell can break loose. So what you have to do in software is then to make sure that before core 1 uses that value, that it is somehow informed that the value here has changed. And that requires a lot of software coordination.
So what happens in a coherent system? How does that change?
Coherent system, yeah. So let's look at the coherent system over here. So here we have again the same two cores as before, except now that the system is now cache-based instead of local TCM-based. So we have tightly coupled caches, L1 cache here for core 0 and a similar L1 cache for core 1. In this system, they both connect to a similar L2 cache as with a non-coherent system. But the difference being that there is Snoop logic that hardware provides that maintains the both local L1 caches in sync with each other. So when any one core updates the value of a variable that is stuck in its local cache, which the other core has read before, just like in the non-coherent case, the Snoop logic ensures that that update that core 0 made will be visible to core 1 immediately before core 1 can use it.
And so a coherent system is basically where you're going to be processing a lot more data, right? I mean, that's the whole idea behind this is you can't do it well with one core. You want to be able to split that up.
Exactly, you're right. So yes, this system here with the coherency is designed for being able to share a lot more data across cores than you would be able to otherwise with a non-coherent system. So because you don't have to do software coordination as much anymore, you're able to allow hardware to do the coordination, and the application can just view the two cores as part of a larger compute block and be able to spread its application threads across those blocks and be able to share data across them quite seamlessly without having to worry about, am I going to be out of sync because I'm running on this core versus that core.
Is it harder to design a coherent system than a non-coherent system?
It depends upon how the vendor of the coherent system provides the IP. What we do in our case is that the entire Snoop logic and the L1 cache controlling and the L2 cache controller is offered as a single package. It's one RTL that people can download, and no need for them to do any other work on their own. It's all done for them. Along with that also comes some other things that are part of the complex, and those are things like debug features, interrupt features, interrupt distribution, and so on. Whether it is inter-processor or coming in from the external world or going out to the external world, all that is offered as a single package. All they got to do is download that, and it's already built for them. And they can then go through the place and route to be able to get to the SoC development. So that's how that works. In the non-coherent case, because it is non-coherent, what people are left with is doing all of that on their own. So they have to do the AXI bus connectivity to the L2 memory. They have to do the TCM connectivity, or even if it's cache-based, they'll have to do that all on their own. And on top of all that, they have to do software on their own as well. Here, what we provide is the two cores run a coherent aware, a multi-core aware real-time operating system that helps to coordinate the data across and the control across the two cores.
So from an engineer's perspective, what can go wrong?
With the system, the cache coherent system, not much, because everything is taken care of for the end customer. The software is provided in terms of the real-time OS. The hardware is provided in terms of RTL. All they can do is download it, go through place and route, and in terms of software, we also provide a simulation tool called the System C. We call it XTSC in our case, and we provide the real-time OS that is multi-core aware. So all the coordination among these cores is handled by the real-time OS.
So what happens if they get out of sync?
There is never a case of them getting out of sync in the coherency case. Why? Because the hardware is at every clock cycle monitoring any updates to any one core, and it also knows if the other core has read that data, and it will make sure that the other core will be informed of that immediately. So there's never a case when the two of them can go out of sync. In the non-coherent case, though, it is quite easy to get out of sync, because in order to maintain synchronization between the two cores, any update from one core has to be in software, updated to the L2 memory, and then read from the L2 memory by the core 1. So there's a lot of manual programming that has to be done to achieve such coordination.
It also has a big hit on performance if they're out of sync too, right? Because you're only running at the slowest, the lowest common denominator, the slowest core.
That is correct. So yeah, basically it is like a pipeline system in a way where your slowest core will determine your final performance. And if your core is bogged down by doing cache updates, just because it has to make sure that the two cores don't go out of sync, and the more often you do that, you have to do that for data, you have to do it for messages, for control messages, and so on. Each time you do that, you're going to have performance hit as well, because the cache flushing itself is a large operation in itself. So you don't want to go through all that every single time. Let the hardware handle all that, and then the software is free to run the actual application.
So let's compare the two of these. What's the upside of the coherent versus the non-coherent, and what's the downside of each?
So a very important question here, Ed. So people have been building non-coherent systems for a while now, okay? So again, that begs the question, why coherent system? Yes, we mentioned one is easier to develop software because you don't have to do the software coordination of flushing the cache and so on. It also makes for better performance, as we discussed earlier, because the big cache flush cycle hit is not something that you incur in the non-coherent system. So it's all done automatically by hardware in the coherent system. The third aspect is, because it is so hard to program a non-coherent system, how do you partition the multiple tasks that you have across these cores? That's not easy to do. you have a certain amount of memory in core 0 and a certain amount of memory in core 1. You have n number of cycles available in core 0 and m in core 1. And you have a set of applications in the form of threads that you want to split across these cores. How do you coordinate that? It's a very difficult task. And architects spend quite a bit of time trying to get the most optimal distribution of tasks across them. And that means, dissecting tasks in such a way that they can be split across, and then sharing of the data and flushing of data and so on. And then once they do all that, the moment you have another application that comes in from product marketing saying, I want this also to run concurrently, now you have to rehash all that and repartition everything. It's a big task and it's a very manual process, a laborious process. It takes a lot of time to get there. So that's one of the downsides of a non-coherent system that is not immediately visible, but those who have done it know that, and we have had a lot of questions from customers as to how do we make that efficient. So our answer to that is the coherent system. So let's go back to the coherent system and see how that looks for this scenario. So in the coherent system, we don't have a fragmented view of memory. We have one view of memory, which is the L2 cache, or L3 cache, L3 memory as the case may be. Any variable or any data or any messages that have been processed or being processed by either core look the same to both cores at any given time. So in a sense, they both see the same value of memory, same view of memory all the time. Okay? And all of that memory is available to every core at any given time. Whereas in the non-coherent case, if you use TCMs, the TCM of one core is not available to the other core. You have fragmentation. So memory that is left over in one core cannot be used by the other core, even if it wanted to use it. If it could utilize it, it cannot use it because of the fragmentation. Similarly, cycles of one core is not available for an algorithm on another core because it cannot be moved across easily. It is not dynamic, so it makes it very hard to get the best optimal performance out of the system. Okay. Whereas here, what happens is, because you have a unified view of memory, and because the operating system can distribute the tasks dynamically between the cores to do load balancing, etc., the entire system gets much better utilized, because if the OS sees that the core 1 has more cycles left over, it can just move the task over to core 1 immediately. It doesn't have to worry about moving the data from L1 cache from here to there, because the Snoop logic will handle all that automatically. So having a unified view of memory helps, and having a unified view of the total compute power also helps to make task partitioning easy across cores.
Where are you seeing this being used in audio? So audio is now an interface in your vehicle. It's an interface in wherever you happen to be, right? I mean, you're talking to Alexa, you're talking to Siri, whatever it happens to be. This is all much more data and much more accurate than it has been in the past.
Yeah, agreed. Actually, the application for a coherent SMP like this spans across all applications, okay? All market scenarios. So think of TWS earbuds. We have customers with TWS earbuds that are supposed to be tiny and small that are already deploying 2, 3 DSPs today, okay? And they're having a hard time partitioning tasks across these cores and making it all run. In fact, they have told us clearly that 2 was a stretch, 3 was extremely difficult, and beyond 3, we don't know how to manage that ourselves. So when you have a coherent system like this that makes software programming easy and optimal for utilization of the resources, cycles, and memory, it's much easier for them to use that. So whether it is TWS earbuds or automotive, people want to utilize a system like this. So in the case of TWS earbuds, maybe it's 2 cores, maybe it's 3 cores. In the automotive case, the demand is even higher. Why? Because they have things like road noise cancellation. They have sound staging. They have in-car communication. They have to listen to alarms from an emergency vehicle, even though you're in a very quiet Mercedes-Benz that doesn't allow noise to come through. So now you want the audio system to listen to the outside world and then alert you that there's an emergency vehicle coming around the corner there. So a lot of these things require more processing and more concurrent processing in the automotive world. The other aspect of it is that most of the cars are now becoming software-defined vehicles. The implication of that is that all of the compute that was in the different zones and the different seats and so on in the car now are going to get sucked into a central compute. So that central compute has to have even more performance than what was there in the different zones. And that also makes it easy for the Teslas and other car manufacturers to be able to do software updates on, later on in the life cycle of the car. So you as a consumer are going to sleep at night. In the morning when you get up, you get an update to your software, and your car behaves differently, your audio behaves differently, and better, hopefully. Why? Because they could actually download the software when you were sleeping, and now your car has a better performance for audio as well. And what does that mean? It means that it's good for them because they can charge you more money for that update. They can keep your vehicle up to date, and they also need 20-30% extra performance available, free performance available, which they can utilize with these updates. If you're already up to the brim of performance for the number of cores that you have, then there's no update possible. So that's why automotive application demands even higher performance, raw performance going out of the gate, which they can utilize with consumers in the field long into the car cycle process.
And when you think about early 2000s, what we heard out of computers and how they talked, it was a radically different sound than what you're getting today. That's just a lot more data that's being processed, right?
Okay, yes, it's a great point. And yes, the audio today is quite different from the audio of our fathers and so on, right? So why? Because the demand for better audio is coming from consumers, and there's also a push from the OEMs to entice customers with better quality audio. So now consumers get used to that, and then they want even higher and higher. So it's a cycle that feeds on itself, consumers demanding and OEMs pushing. And so what you're seeing now is that what used to be mono and stereo earlier has become sound staged in the automotive world as well as in your TWS earbuds. When you're walking around with earbuds on and listening to music or jogging, you're carrying with you now the entire sound stage that the New York Symphony Orchestra was providing. So now we have algorithms, for example, that can take any audio that you have, that you're playing back, that was old stereo, which maybe not more data, but you can now upscale that on the fly to sound like it's coming from the New York Symphony Orchestra while you're jogging down the road here in your neighborhood. So once you get used to that, you're never going back to the old way again.
Prakash Madhvapathy, thanks for a great explanation.
Thank you very much, Ed, for having me. Appreciate the opportunity.